acid and base equilibrium. Right? So it's a subsection of equilibrium. And first we got to cover some, oh, I wonder how about that post-it note, because I've always wondered that.
You wanted it or you don't?
No, I have wanted it in the past and not know how to do it. And there it's appeared.
Got it.
Oh, or we could just cancel the whole system. Okay, so acids and bases. Definition empirically, meaning in the lab. Bases are slippery, you've already said to me. Okay, so we'll put that down. Anything else?
Above 7.
Bitter. Okay, slippery. Bitter. They have a pH of
Above 7 to 14.
No, incorrect. First of all, they don't have a pH of 7.
8.
That's neutral. And second of all, it can go above 14. What? Shock? Horrible.
No,
7.1 plus.
It's not on the scale.
What about 7.01?
Is
Don't you just say it's
greater than or equal?
Why don't we say it's greater than 7?
Equal, yeah.
Why don't we say it's greater than 7?
Or equal, it could be equal. That'd be neutral.
What about litmus paper?
Turns red.
Red litmus turns blue. Okay, that might be enough. Acids. Sour. Like lemons.
pH below 7.
pH of less than 7 or below 7 if you want to write it in words. Blue litmus will turn red. Okay. Everybody okay with all those? All right, so that's all your stuff about kind of junior high acids and bases is in there. Okay. Empirically, meaning the lab. So if that was the first time that you have seen that word, you think, memorize it now. Okay? Theoretically means in theory, not in the lab. So when the scientist said, hey, what's the difference between acid and base? Okay, we learned about the theory. So things you can't see or really test directly for. So Arrhenius is somebody that I hope you covered in Chem 20. Hands up if you remember the word Arrhenius.
Nope.
Okay, so a couple of you. So Arrhenius is like, ignore the word Arrhenius and just tell me what makes an acid, do you think?
H+.
It has H plus in it. That's Arrhenius's definition. Okay? Contains H plus. Like what? For example,
Hydrochloric acid.
HCl. For example, H2SO4.
So it's like what makes an acid and a base a base.
Kind of. In like Chem 20 knowledge. Okay?
Junior class change.
So what makes a base, do you think? OH minus. So this is when you see this chemical symbol HX, and I were to ask you is it acid or base, you would guess that it's a acid because it's going to contain the H plus, right? And if I said we have a base that's XOH, you would think it, or I mean, if I said that here's a chemical XOH, is it acid or base, you would probably think base because the OH minus. Okay. So it contains OH minus, for example, sodium hydroxide, calcium hydroxide. What about C, because this is the one they give you that throws you off, something like C2H5OH. Is that a base? No, why not?
It's an alcohol.
It's an alcohol, and it doesn't contain OH minus. It doesn't contain hydroxide. Right? It's a hydroxyl group, but it's not hydroxide ion. Okay, so that's the throwaway, that's the distractor in a multiple choice question. And in fact, actually, I give this in a multiple choice question to my Chem 20s, and this is the distractor. Find the base. One of these, one of these, one of these, and probably like NaCl. Okay. Okay, but here's the thing about Arrhenius's definition, or the simple junior high science 10 definition, is that something like ammonia gas, NH3, has a pH of greater than 7. Would taste, although I wouldn't suggest tasting it, would taste bitter, is slippery. So why is and neutralizes an acid. Why does it empirically act like a base, but it doesn't have any OH minus in it? So scientists had to go, Arrhenius, you're right for a lot of things, but we need to modify your theory because there's some exceptions to your rule that don't really fit into play. Okay? And those scientists were Bronsted and Lowry. And they have come up with a better definition that includes all of these and or exceptions. Do you remember Bronsted Lowry? A little bit from Chem 20. Okay, so in Chem 20 they don't often say Bronsted Lowry, they say the modified theory to keep it a bit more simple because they think that names are scary or something, I don't know. But the modified theory or the Bronsted Lowry concept is that acids are proton donors where, what's a proton?
A positively charged ion.
Positive charge ion. And what can you tell me about, well, I can't remember if I did this in my Chem 20s or my Chem 30s this semester. H plus? What is it? What's in its nucleus?
Positively charged.
Like if you go back to Science 10, how many protons in H plus? 1, because you look at the atomic number is 1. How many neutrons? None, because it's 1 minus 1, so 0 neutrons, right? How many electrons did it have when it was H atom neutral? 1 electron, right? But then to become H plus, it must have lost that electron. Have I done this with you this year? No. So what is H plus then? It's just a proton. Look, it's just a proton. It's got no neutrons, it's got no electrons. It's just a proton. See? So we say proton donor, and what we mean or what we see is an H plus donor. Or it gives H plus away. So, hold on, HCl, does it give H plus away? Could it give could it dissociate an H plus and then give that H plus to a base to neutralize it? No. Yes, yes, yes. Okay? So we say proton donor, but when we mean proton donor, we mean an H plus donor, which fits in with Arrhenius's definition that it has an H plus to give away if it needs to. Okay? Yeah.
Does that mean that technically an element has an H plus?
No. A proton by itself. Okay? If the proton has a bunch of neutrons with it in its nucleus, it can't donate a proton by itself. All those nucleuses will go along, or neutrons, I mean, will go along with it.
So is that why when like you react carboxylic acids with bases, carboxylic acid gives the H plus and the base gives the OH?
Right. Right. Connections. So hands up if you've never seen this before, because I'm getting the vibe that you've never seen this before, this proton donor. Jacob, put your hand down because I taught you Chem 20. Okay. All right. So this is a concept in Chem 20, and yes, it applied when we were learning about our reactions about carboxylic acids, where we donated a proton or donated an H plus across. Okay. So hopefully, if that was a bit shaky for you, hopefully this unit will help solidify that. Right, bases then will be proton acceptors. Meaning they receive an H plus. Okay? So they are proton acceptors, meaning they receive an H plus. Everybody okay with those definitions? Proton donor, proton acceptor. So for example, HCl. I've got one kind of normal example. So scientists will say, right, this is our new definition. Does it still apply to the old theory? Because it should, because the old theory sounded pretty good. So we don't want to just throw it out. So does it still apply to the old theory? Is HCl a proton donor? Does it have a proton to give away to somebody? Yeah, here it is. Check, works. This is still a proton donor. Okay. In fact, actually, did you not learn that HCl must exist as aqueous in order to be an acid? This is why. HCl must be aqueous. What's with it when it's aqueous? Water. So who is it going to donate its proton to? The only thing that's there, which is water. So here we go. I'm going to donate this proton, H plus and Cl minus. I'm going to donate this proton to the water. That water used to look like this. Everything okay? Now it looks like this. So it's H3O plus, which is called hydroxonium ion. I think it's hydroxonium. It is hydroxonium. It might be something slightly different in your syllabus. I will look to see if it's different. Just hydronium? I'll look. It is called hydroxonium, so I'm going to leave it there because it's not incorrect, but your syllabus might call it something slightly different. And what's left over then? Cl minus. So who donated the proton? HCl. Who accepted the proton? The water. So what is, by definition of Bronsted-Lowry, a base here? Water. So water has accepted, so this is that acid that's fine by Arrhenius or Bronsted-Lowry. This is now a base because it's accepted the proton. And, by the way, that's why HCl is only acidic when it's in an aqueous solution. Because it has to donate to somebody.
Well, and technically, like water can be written as H double H, right?
Yep.
Are there any are there any more compounds that fall under that aren't like a well-known base? Like, cause like you wouldn't think of water as a base.
Oh, you're about to see a lot of them.
A lot of them.
Yeah. Okay? And hopefully, instead of thinking of it as a list to memorize, you see it as, oh, it must have accepted a proton here. Look, I've gone from H2 to H3 plus. So I've gained an H plus. Therefore, I've accepted an H plus. Therefore, it's a base. So you see it more as a pattern. Like a Lego block has been taken off of this and put onto that. And this is now bigger by that one Lego block. And therefore, it must be based. Okay, so that's how we have to start seeing it. Not as a list to memorize, but as a, oh, that chunk went over there. Therefore, donated, accepted. And then I can apply it to X, Y, Z, because you know how much they love doing that. Qs and stuff like that. Right. Okay, so I've written a lot of, right. So CH2CH3OH is something that you saw in the acetic acid subunit of the organic. And again, we reacted that with water. And we got, so Arrhenius would say that that's not an acid. Arrhenius would say this is not an acid. There is no H plus there. So we have to use the Bronsted-Lowry definition to show how we're getting it to donate a proton. Okay, there is no H plus, there's an H, but no H plus, it's a shared pair of electrons. Okay, so this is going to donate a proton to there, right? In fact, I probably should write it above that H. And what does the water become? H3O plus. And the rest is the CH3CH2COO minus. So this is an acid because it's donated. This is a base because it's accepted. Bless you.
But why would the reaction want to do that? Because then they're too unbalanced.
What do you mean there's two unbalanced?
Like they're ions. Aren't they more stable if they're?
No, not necessarily. Sodium ion is more stable than sodium solid.
They're more reactive with that electron.
Okay? And then ammonia. So ammonia, I told you, has all these properties like a base, right? So let's see what happens when we put it with water. I told you it acts like a base. So I told you all the empirical properties make it a base. Can you get it to accept a proton then? Because that's by definition what a base is, according to Bronson-Lowry. Accepts a proton. What will it look like if it accepts a proton? NH4 plus. Have you seen that before? Oh yeah, ammonium. And what does the water become? OH minus.
So the water's
That's where the OH comes from. Back to the Arrhenius.
So water's being as
So in this case, water is an acid. So you're right. Water can act as an acid or a base. It can donate or accept a proton. And that's called amphiprotic, which is a definition on the next sheet. So don't worry about writing that down. Yes, Daria.
How was NH3 the proton accepted this time?
Well, first of all, because empirically it told us it was. Right? Evidence said it acts like a base.
Okay.
So let's get it to accept a proton.
So we just should know that.
Well, I told you that. It's a paragraph. But equally, have it donate a proton. Let's just pretend for a minute, as scientists, we have no idea. We're going to take NH3 and we're going to treat it like an acid. It would become what if it donated a proton? NH2 minus. Does that look normal? No, because it's not. It's incredibly unstable. So that's not going to happen. So this happens. Because that's stable and that's stable. And that's stable and that's stable. Okay? By the way, I used equilibrium arrows here, equilibrium arrows there, because those are weak acids and bases. And here I used 100% arrow because it's a strong acid and base. I don't know if I actually did, but I should have. Sometimes I'm thinking about the bases. Okay, any questions on those examples? Greg, are you paying attention, please? Okay, so what we're going to end with in the next 15 minutes is, did you notice all those H pluses and all those OH minuses? All right, and in Chem 20, not only did you learn about the modified theory, one would hope, but you also, one would hope, did calculations about H pluses and OH minuses. Do you remember doing those? Yes. Okay, so there are only a few formulas that you use, right? So, and you need to memorize them, but they're all kind of tied together, so they're not very difficult to memorize. I don't think anyway. So, oh dear me. One formula is pH equals negative log concentration of hydrogen. Okay? So in your calculator, you put the concentration of hydrogen, like 1 times 10 to the power of -3. You hit the log button, and you times that by -1. Presto. Okay? And similarly, POH equals negative log OH minus concentration. So do you see how those two formulas are really just one thing to memorize? And guess what? K equilibrium equals negative log K equilibrium. I'll say that again. K equals negative log K value. You see how I can chuck anything in those spaces there? Okay? All right. So those are two formulas from science or from Chem 20. And then the opposite of that, so this rearranged, in other words, like dividing log by both sides, except for you don't divide log because it's a function in itself. It's not multiply. It's not divide. It's not add, subtract. It's log. So you have to take the inverse of log. Now, luckily on your calculator, you can see the log button, and you can see the blue writing above the log button, you know, the second inverse of the log, is 10 to the power of. Because that is what the opposite of log is. So, in order to find the hydrogen concentration, if you're rearranging this top formula into this one, you would go 10 to the power of negative pH. Everybody okay with that? So this is the opposite of each other. That's like a rearrangement of the formula. And so I'm going to rearrange this formula as well, and I'm going to say the OH minus concentration equals 10 to the power of, follow the pattern, negative POH. See? So far, really, I've only memorized kind of two things. And one of which I can get a hint off my calculator. Next formula to memorize is, this is kind of an easy formula, students tend to like this one, that pH plus POH, in fact I'm going to write it over on that side so that I've got some room to write underneath it. pH plus POH equals 14. Because the pH scale is up to 14. And so, apparently, yeah, it's a Chem 20. And so the POH and the pH are the opposite ends of the time, of the number line from each other. So if you have a pH of an acid at 2, the POH must be 12. 14 minus 2. Okay? And the rearrangement of that, involving these logs, ends up being that the concentration of H plus times the concentration of the OH minus equals 1 times 10 to the power of negative 14. Where's that 14 come from? The pH scale. Why is it 10 to the power of negative? Because here it was 10 to the power of negative pH. So all those formulas kind of tie in together. And you're using all those formulas in a different way, actually. So Raj might start by using this formula and work his way over here. Somebody else might start by this formula and work their way over there. You should still get the same answer, regardless of what pathway you go along, because all these formulas are linked. Okay? So for the next 10 minutes, I'd like you to do this chart, which covers all of those equations at some point in the chart. It's a really good summary of your Chem 20. Do you know your pH stuff? Okay? And yeah, there are questions on the diploma that say the pH of this is blah, blah, blah. What's the POH? What's the OH minus concentration? Just like there was in Chem 20. So, you know, this is, you've got to know this stuff. Don't just do it and hope that it's not going to be there. Okay? All right.